A very good morning and welcome to this course on the foundations of continuum mechanics. Today we start with the third module of the course, that is the module on kinematics. So let us get started with this lecture. So the topics for today's lecture are as follows. We will talk about the idea of a material body and configurations of particles which form a body. And then we'll talk about motion, particularly about deformations, which are important in the field of continuum mechanics. Kinematics is the study of motion. And in general, in mechanics, we want to quantify motion as a result of some external force or stresses acting on the body. So in continuum mechanics, we link stresses with strains or rate of strains, which are quantities which are used to quantify motion in this field. So stress is related to the strain or the rate of strain, or sometimes both. So typically strain is studied in the field of solids or solid mechanics, and rate of strain is typically studied in the field of fluids. I say typically because there are solids which flow, that is, they continuously deform with time, that is in plastic flow, and there are complex fluids which demonstrate the behavior of yielding, where they behave like solids for some region of stresses and then start flowing like a fluid. So in this module, we learn how to specify these quantities, that is strains and strain rates, to specify motion in continuum mechanics. So this week is very important because this sets the foundations for the various quantities that will be defined in the next 2 weeks. So now we talk about material bodies and configurations. So let's say we have a material body, which could be a solid, could be a fluid or a gas. So even a fluid like liquid can be written as a collection of particles of material, in this case particles of fluid. So we'll have a particle lying at a position here, so we'll call this particle A, and then another particle, particle B, which lies here at some time t equal to 0, which is at some initial time, or we say that this is an initial configuration. And then at some later time t, we will notice that the particle A has moved here, let's call it A prime, and the particle B may have moved here, which will be called B prime. So this is at a later time, let's say t1, and since this is a different configuration of particles, so we can call it a deformed configuration. So there is a one-to-one correspondence between the position of particles, that is, there's a one-to-one correspondence between A and A prime and B and B prime. So what that means is that the particle A at a later time t1 will be at one unique location. It cannot be present at multiple locations. And similarly, particle which is at A prime is coming from a unique location at t equal to 0, that is from the location A. Now this is a subtle but an important idea in developing the theory of continuum mechanics. So we must remember this basic assumption so that we do not confuse ourselves later. So I mentioned that there is a one-to-one correspondence. So we just talked about the word configuration. So let's define it properly. So a configuration is defined as a relative arrangement of material particles in a body. So for instance, if I have a body and I change its shape, I can easily see that this new shape is a new configuration because the relative arrangement of the particles has now changed. Similarly, if I try to expand the body or contract the body, even then I see that the relative arrangement has changed. So this results in a new configuration. In continuum mechanics, we talk about different configurations to quantify the motion or particularly deformation, as we'll discuss soon. By the way, there's a confusion sometimes that it is only solids which can deform. That is not the case. Fluids also deform. In fact, fluids deform continuously, because if you take a fluid and you apply a shear stress to the fluid cannot resist it. It starts deforming and flowing. So flow of a fluid can be thought of as a continuous deformation. I'll just show that to you through a diagram. So let's say this is an initial configuration in a fluid when it is at rest. So I have different particles in the fluid, which I call material particles. And this is again for understanding in continuum mechanics. These material particles can be thought of as a collection of fluid. Now, when we apply a shear stress to the fluid, it starts to flow. So what I'll notice is that this collection of particles will have a different shape at a later time, where the top particles would have moved more than the bottom particles. So this results in a relative change in shape of the fluid material body. If I wait for a longer time, I see the top particles have moved a further distance, the bottom ones have moved a smaller distance, so the overall shape of the fluid feels or looks even more stretched. So here's a particle A, which becomes A prime, which becomes A double prime, and so on. And relatively, you have a particle B, which becomes B prime, which becomes B double prime. So we can see that the relative arrangement of particles A and B definitely changes with time in a fluid as well. So the theory of continuum mechanics is very much valid for fluids as well as solids. So we have been talking about material body. So let's define that properly as well. So a material body that we have been drawing, we'll denote that with a B sometimes, is a collection of particles or material points, or sometimes also called material particles, which we have been showing with these dots inside the body. And all these particles correspond to a physical location or a position in the physical space. And since we're talking about continuum mechanics, all these particles are continuously distributed. So what that means is that if I have a body like this, and all the points in the body will be defined with respect to the O, x1, x2, x3 coordinate system, then a particle P exists here and there's a particle Q both inside the body, then between these two particles I have infinite number of particles of the body, and each point between these two points P and Q corresponds to a physical material particle of the body. So this is the idea of a continuous distribution of particles in the body. We cannot have a situation where there's one point missing where there's no particle. Body is assumed to be continuous in the sense that within the boundary of the body, all the material particles are continuously distributed. So if I just talk about the point P, then this point P will have certain coordinates in the physical space. That will be x1, x2, x3, and since we're talking about the particle P, we'll put a superscript P over them to specify that these are coordinates of the particle P. And the position vector for particle P then becomes x vector with a superscript P. So this P here denotes a material point or a material particle. As I said, there's a one-to-one correspondence between physical particles and positions in space. So let's identify the particle P with its ID. So this capital X P is a particle ID. It could simply be a number. and this corresponds to a position vector in space in the OX1, X2, X3 coordinate system that we have chosen. So there's a 1-to-1 correspondence between the particle ID, capital XP, and the position vector, small xp. So there's a 1-to-1 correspondence between capital X and the small x vector. Now, till now, we've been talking about masses, but these material particles or points do not have a mass because they exist at a point. So instead of a mass, they will have a density associated with them. So given a density field, which is rho as a function of some x vector, I can find the density at the point P or for the particle P as the rho function for x p vector. Again, these are some basics one needs to understand to be able to develop the definition of more complex quantities like strains and rate of strains. So now that we understand these terms, we can quantify the idea of a configuration. So a configuration now can be expressed as a mapping or a function. Let's say the function or a mapping kappa as a function of the particle ID. So I have a configuration like this. So if I pass in the ID of a particle to this mapping or a function kappa, it will give me the position, the x1, x2, x3 coordinates of the particle P. So in general, I don't need to write a P here. I can simply say that the mapping kappa represents a configuration. So in this mapping, I can pass in the IDs of all the particles in the body and I get the positions of all the particles in the body. And as the configuration changes to some other configuration, I will see that this will correspond to a new kappa, because as I pass in the IDs of the particles, they'll have different positions in the new configuration. So this kappa corresponds to a configuration. So it's a mapping or a function corresponding to a specific configuration. So we see that we pass in the particle ID to the mapping function kappa and we get a position vector corresponding to that ID. So this kappa is actually a vector function, which means that the output of this function is actually a vector, which in this case is a position vector. I've just written that different configurations will have different kappas or mapping functions. Now, because we said that there is a 1-to-1 correspondence between the particle ID and the position vector, so I can define an inverse mapping as well, because for every position vector in space, we'll have a corresponding particle ID. So the inverse mapping is, we'll call it kappa inverse, where you pass in the position vector and you get the particle ID as a result. So this kappa inverse is called the inverse mapping. So now that we understand the idea of configurations and how to quantify them using mappings kappa and kappa inverse, we can start talking about motion and particularly deformation. Mechanics is all about studying motion, and motion can be a rigid body motion or it can be a deformation. So till now we've talked about rigid body motion, where initially we had the body translating and then we studied rotations as well. So in a general rigid body motion, we could have the center of mass translating and the body rotating as a whole. But that is not the end of it, because realistically speaking, when we apply forces, particularly stresses to bodies, the bodies deform. Let's take an example of a rubber ball. If you press a rubber ball, you will notice that its shape will change. That is, it will deform. And this deformation cannot be studied using rigid body motion. So we require some metrics or some quantities that can measure this deformation. And these 3 weeks are all about quantifying those geometrical objects. So before we talk more about deformation, let us draw some diagrams to clarify the ideas further. So in translation, let's say we have a cube. It translates to a new position like this. So this was the center. This is the new position of the center, and there is a change in position. The position has changed. Of course, the position of all the particles have changed, but I've only shown the center of the cube. Now let's talk about rotation. So let's say we again have a cube with the center as C, and then the cube undergoes a rotation. So this results in the cube now looking like this with the same center, but we'll call C prime because that is for the rotated body. So the center coincides, but if I take another point, let's say on the top right of the initial body A, it has moved to this location, which is A prime. So we see that A moves to A prime. So the orientation has changed. Now let's take our cube again with the center C. And this time the body will go through a shape change like this. So we notice that the point C has moved to C prime, and so has a point A, which has moved to A prime. So this is a change in shape. In deformation, we can also have a change in size. So we notice that the body compresses overall, and this is called size change. So instead of compression, we can also have expansion. Now, in a general deformation, we could have both, that is, both shape and size can change. Some more terminology. So this shape change situation, where the body purely changes the shape, is called an isochoric deformation. That's a more technical term for pure shape change. So this isochoric means that the shape changes, but the volume stays the same. Isochoric basically means constant volume. So this is a shape change, but same volume. This is also known as distortion in the body. And on the right hand side, where we have a pure change in size, is technically called dilatation, or colloquially, it's simply called dilation. That is, when volume changes, but the shape does not change or shape stays the same. And again, once we define strain, we will learn how to quantify these ideas into geometrical quantities. So we will mathematically be able to concretely define these ideas of isochoric deformation or dilatation. Or more generally, we'll have both. So we'll learn how to split this into a pure volume change and a pure shape change. And by the way, a general motion that we just talked about as rigid body and deformation, a general motion can have everything. A general motion can have the body translating to a new position, that is, the center of mass moves. It can include rotation as well and deformation as well. It is just that we study them separately in general. So in the field of continuum mechanics, we will generally be interested in the deformations, not the translation or the rotation. But in the subject of mechanics, you should be able to find everything, that is, its translation, its rotation, and its deformation of different types, which includes volume changes as well as shape changes. So let's now try to quantify the idea of motion using the ideas of configurations and the mapping function. So I'll just draw a diagram to show you that the body can take different configurations. So let's say initially the body is oriented like this, and then it moves to this configuration, and then maybe it changes its shape, and then maybe it shrinks into a smaller volume. So you see that a lot of things are happening over time. And if I track one particle, let's say a particle P, that particle P will go to different positions as the body moves. So we say that the particle P has some trajectory. And if I was doing an experiment where I highlighted the particle P using a fluorescent tag, I would be able to see its trajectory through a specialized camera with some lighting. But we are interested sometimes in not just the particle P, but the whole body's movement. So we say that the body B undergoes a sequence of configurations. It's an important idea of sequence of configurations. So all these are configurations. Of course, I have shown them at discrete snapshots in time. In a continuous sense in time, you will see the body continuously deforming from one configuration to the others. So earlier, we talked about a configuration being represented using a kappa function, where you pass in the particle ID and you get its position in space. But now when the motion's happening, you will see that a particle ID, that is, for example, P in the case above, will continuously change its position in space. It may stay stationary, but in a most general sense, it will continuously keep moving in the spatial coordinate system. So I have to modify my kappa function, which is now a function of two quantities. One is a particle ID and the other is time t. So if I specify a particular particle, let's say q in this case, I get the complete trajectory of the particle q, because this function will return the position and I can plot the positions in space at different times t by passing different time values to this function for the same particle ID for q. And because there is a one-to-one correspondence between the particle IDs and their positions in space when we talk about material bodies, so we can also define an inverse mapping or an inverse function where we pass in the position coordinate and time, and that tells us that at a given time t, at a given position x vector in space, I have this particular particle with this ID sitting there. Again, you cannot have two particles sitting at the same position in space. So there's a one-to-one correspondence between particle IDs at different times and their position in the physical space. Of course, at different times at the same physical position, you may have different particles. In fact, you will have, as the body moves, different particles will travel to the same position in space at different times. But for a fixed time value at a given position in space, only one particle can exist at that point. So this kappa function contains information about the complete sequence of configurations. So earlier, when we had a single configuration, we had kappa being a function of ID, but when we bring in the effect of time, we can now represent a complete sequence of configurations. With these ideas, now we can define something called an initial configuration, and it's quite obvious that it is that configuration which corresponds to the body at t equal to 0. That's initial. Now, once I put a specific value of t in this kappa function, I get one unique configuration, which we call the initial configuration. That's a terminology. In continuum mechanics, we would want to define something called a displacement field. That is, we want to define a displacement of different particles. But to define displacement, we must know some reference position. Displacements can only be defined with respect to some reference. So the configuration of the body, which is used to define displacements, is called a reference configuration. So let's say we decide that this configuration is the reference configuration, and now the body deforms and it takes this configuration, the green one. A material particle was at this location, let's call it A, which in the green configuration has moved, let's say, to this position. So this is A prime. So there's a displacement of the particle, which we denote by the vector u superscript A, which is called displacement of the particle A. So you can see that I was able to define a displacement in terms or in reference to a reference configuration. That's the black one here. Well, a most obvious choice for a reference configuration is the actual configuration of the body at t equal to 0. So the initial configuration is the most common choice for the reference configuration. Now please understand the difference. Initial is the actual configuration of the body that the body assumed at t equals to 0. But the reference configuration is our choice. We can choose the configuration of the body at any time as the reference. It is our choice. In fact, we can assume a hypothetical configuration which the body never assumes and still call it a reference configuration. But that is something we don't usually do. So we stick to the initial configuration as the reference configuration, but you must understand the difference in the terminology. So we have defined initial configuration, reference configuration, and there is another term that's called current configuration. So current configuration is the configuration at time t current. So if we're talking about now, then the current configuration would be the configuration of the body at right now. So generally, kappa of particle ID comma t is the current configuration. In continuum mechanics, when we are defining strains, we usually talk in terms of only two configurations. The first one is called the undeformed configuration, and the second one is called the deformed configuration. So undeformed is the one which is before deformation, and deformed is the one which is after deformation. Now this event called the deformation event may happen in an infinitesimal time. And if we have the body going through multiple configurations, we will talk about the first and the second, and then we can have a sequence of configurations where the current configuration is the deformed one and the one just before that is the undeformed configuration. So at this stage, it is not important why we just talk about two, but what is more important is the terminology here, that there is something called an undeformed configuration and there is something called a deformed configuration. So if we have just two configurations, let's say the undeformed one and the deformed one, so let's call this 1 and 2. So a particle A in the undeformed configuration goes to A prime in deformed configuration. So this allows us to define a displacement u for particle A. And all the positions have to be defined in terms of a chosen coordinate system. So this brings us to the end of our discussion in today's lecture, where we talked about material bodies, configurations, and deformations. We quantified configurations using mapping kappas, and we defined deformation as a sequence of configuration, that is the body going through a sequence of configuration. However, we said towards the end that we are usually interested in just two configurations. One is an undeformed one and one is a deformed one. So with this understanding of the terminology, we are now ready to define material and spatial coordinates. So let's do a quick exercise, a very intuitive exercise, which will set the foundation for next lecture. So let us say we have a body in this undeformed state where it has certain dimensions with this coordinate system, and then the body deforms, it sort of stretches in one direction and the width decreases with these new dimensions. I'll also highlight the coordinate system again. So the question is, how do we quantify this deformation going from the undeformed state to the deformed state? As I said, we'll discuss this in a proper logical fashion next time, but let us discuss this in a very intuitive sense. So let us say that small x denotes the position of a particle in the deformed configuration, and capital X, vector this time, this is different from the particle ID by the way, denotes the position in the undeformed configuration. So I have to specify that my x1, small x1, is, in this case, let's say L by L naught times capital X1, and small x2 is H upon H naught times capital X2. So a point P which had coordinates capital X1P comma capital X2P will have moved to a point P prime which will have coordinates small x1P comma small x2P, where the relationship between these two coordinates is given by this mapping. So this was a quick peek into what we'll discuss next time. Thank you very much, and I'll see you in the next lecture.